For much of modern neuroscience, the brain has been treated as a machine for thinking, perceiving, and deciding, with bodily regulation relegated to a supporting role. This paper turns that assumption on its head by arguing that the brain's primary job is not thought at all, but prediction driven regulation of the body. From this perspective on, cognition, emotion, and perception are not the drivers of behavior, but the visible outcomes of a deeper biological task, namely anticipating future demands and allocating energy before imbalance occurs within the body. What we experience as a thought are therefore not the cause of action, but the consequence of a brain whose core function is to keep the organism alive by staying one step ahead of its own physiology. This paper advances a fundamental reframing as to how brain functions should be understood, arguing that allostatic rather than the cognition itself or abstract thought lies at the core of what the brain does. Traditional neuroscience has been centered mental life around perception, decision making, and conscious thought, treating bodily regulation as a background or supporting process. This work, however, challenges the hierarchy and proposes that the brain's primary role is to regulate the body in a predictive manner, hence the intuition thoughts, with thoughts and emotions and perception emerging as downstream consequences of that regulatory task. At the heart of this paper, there's a distinction between homeostasis and allostasis. In homeostasis, we refer to the reactive maintaining of internal variables within a biological body, such as correcting deviations in temperature or blood glucose after they occur. On the other hand, allostasis is an anticipatory phenomena. It involves predicting future needs as an intuition and adjusting the physiological system in advance in order to meet those upcoming demands. The authors here argue that the brain evolved primarily as a allostatic organ, one whose core function is to manage energy and bodily resources efficiently over time rather than merely reacting to what is out there. This predictive regulation requires an integration of information across multiple timescales. The brain then must combine sensory input from the environment, introspective signals from within the body, as well as memories of past experiences and expectation about future context. These integrated signals allow the brain to estimate upcoming metabolic cost and to coordinate physiological systems accordingly. From this perspective, cognition is not an abstract computational process detached from the body, but a biological grounded mechanism for anticipating or managing energetic demands of the future. This paper emphasizes that survival depends less on reacting accurately to the present moment and more on preparing effectively for what's about to happen. An organism, for example, that waits for physiological imbalances before responding risks falling behind environmental demands. In this case, allostatic regulation enables the brain to shift, for example, cardiovascular activities or hormonal releases or immune readiness, etc., ahead of time. These preparatory changes often occur before conscious awareness, suggesting that what we experience as a thought or emotion is frequently an interpretive layer applied after the body has already been mobilized. A key implication of this view is that mental states cannot be fully understood without reference to bodily regulation. For example, emotions are often treated as subjective experiences or behavioral responses. Within an allostatic framework, on the other hand, emotions reflect predictions about bodily needs and resource availability in the near future. Fear, fatigue, or motivation arise when the brain anticipates certain energetic costs or risks in the near future to come and prepares itself and the body accordingly. So, subjective feelings become a readout of predictive regulation of the near future rather than its cause. The authors here draw attention to the anatomical organization of the brain to support this claim. For example, brain regions traditionally associated with higher cognition are densely interconnected with areas involved in autonomic control or interception. These connections suggest that cognition and bodily regulations are not separate systems, but they are component of a unified predictive machine architecture. The brain's network do not cleanly divide into thinking versus regulation modules, but instead from overlapping systems that jointly support the allostatic control. In other words, everything about predicting what is about to come. This predictive machine of a brain framework also reframes perception itself. Sensory processing is not merely about constructing an accurate representation of the external world, but about extracting information relevant to future bodily needs. Visual, auditory signals, etc., are interpreted then in light of their implications for action and energy expenditure for the body. What an organism perceives as salient depends on predicted consequences for physiological regulations, not an objective stimulus properties alone. Learning also plays a crucial role in refining the allostatic predictions within the brain. Through experience, for example, the brain updates its mental models of how environmental cues map onto bodily costs and benefits. Habits, expectations, and even cultural practices shape these predictive models within the brain over time. As a result, individual differences in thought patterns and emotional responses can be understood as differences in learned allostatic strategies within the brain rather than purely cognitive traits of the brain. Stress and pathology is also in focus here, where chronic stress here in this paper is framed not as excessive emotional reaction, but as a prolonged allostatic demand. When predictive models within the brain, for example, repeatedly fail, or when the environment imposes sustained uncertainty, the brain must continually adjust physiological systems at very high cost. This persistent regulatory effort leads to allostatic load, a cumulative burden of bodily systems that contributes to a wide range of physical and mental health conditions. From this perspective, disorders such as depression, anxiety, and metabolic diseases can be understood as failures or inefficiencies in predictive regulation. Rather than localizing dysfunction to isolated brain regions or neurotransmitter systems, the allostatic model emphasizes system levels breakdowns in forecasting and resource management. So symptoms emerge then when the brain's predictions no longer aligns well with actual bodily needs or environmental demands. Researchers here also connect their argument to broader predictive processing theories in neuroscience. Predictive coding and active inference frameworks propose that the brain continuously generates predictions and updates them based on error signals. So the allostatic perspective extends these ideas inward, highlighting that prediction applies not only to sensory input but also to internal physiological states within the body. So error minimization becomes a matter of balancing energy budgets and maintaining long-term viability rather than merely optimizing perceptual accuracy. This paper also cautions against equating intelligence with abstract reasoning alone. Intelligence, or biological intelligence here, is the ability to manage resources across time under uncertainty. Thought then becomes one tool among many that serve this deeper regulatory function. This challenges the common assumption in both neuroscience and artificial intelligence that place reasoning or symbolic manipulation at the center of intelligent behavior. And so it is not the thought itself in the brain that matters most, but the underlying regulatory process that gives rise to it. Thought do not drive the body so much as to the body's regulatory needs shape which thought arise. So conscious experience becomes an interpretive narrative layer on top of continuous physiological forecasting and this predictive behavior of the brain. This perspective has implications beyond neuroscience in extending, for example, into psychology or medicine and even philosophy of mind. It suggests that understanding human behavior requires studying how brains manage bodily uncertainty rather than focusing narrowly on mental representations. It also implies that interventions aimed at mental health may benefit from targeting bodily regulations and predictive stability rather than cognition alone. And so this paper offers a unifying account as to the brain function that dissolves traditional boundaries between mind and body. By placing allostatic at the core of neural organization, it reframes cognition as an emergent property of biological regulation. The brain is not primarily a machine for thinking, but a system for anticipating, predicting, allocating, and conserving the resources that make thought possible in the first place. This allostatic framing maps naturally onto the core premises of symbiotic intelligence, which treats intelligence not as an abstract computational property, but as a dynamic regulation process embedded within the biological system. For example, if the brain's primary function is predictive regulation of the body, then intelligence itself is fundamentally embodied, physiological, and context dependent within the body and the brain. Symbiotic intelligence then extend this insight by proposing that future artificial systems should not merely model cognition or behavior at the surface level, but should interface with the same underlying regulatory signals that give rise to thought in the first place. So rather than building AI systems that simulate reasoning in isolation, symbiotic intelligence focuses on integrating real-time biosignals such as neural oscillations as primarily input, aligning AI system with predictive energy managing logic that governs the living intelligence as we know it today. From this perspective, symbiotic intelligence is not about augmenting human thought, but about coupling AI systems to the same allostatic loops that shape perception, emotion, as well as decision making in biological organisms. By interfacing with bioelectrical, for example, signals, this system could learn to anticipate needs, adapt to internal states, as well as regulate responses in ways that mirror how the brain actually operates. And so this represents a shift from AI as an external tool towards AI as a co partner in the system, and where it looks at the what the environment has to offer and what the body itself is demanding. In this sense, symbiotic intelligence is a direct extension of the allostatic brain framework, translating its biological signals into a design principle for these upcoming, for example, artificial systems. And that's all I had for today. Thank you guys for watching. I'll see you guys next week. Bye.